A differential equation for capacitor discharging in an RC circuit. Here we derive the equation for the charge on the plates of a discharging capacitor as a function of time. The capacitor C has already been charged, let us say, such that the initial charge on the capacitor is Q, with the plates having equal and opposite amounts of charge, as shown in the figure. There is also a resistor of resistance R in the circuit, but as you can see, there is no longer a battery. When the switch is thrown, a time-varying current, I, or I of t if you wish, will begin to flow into the circuit. We're going to close this switch here, and we're going to get a current that starts to flow, and it's going to flow away from the positive plate and toward the negative plate. We're going to call it little I, or I of t if you want. Starting at the dot and traveling counterclockwise, recall that our current is going like that. We've closed the loop here. And let's write a Kirchhoff's loop equation for the capacitor discharging, which obviously is when the current is flowing. Our equation should end with equals 0. Also recall that the charged capacitor initially has the potential difference Vc across its plates. We start here and we go counterclockwise around the circuit. Whenever we go through a capacitor in the direction opposite its electric field, we end up with a positive V sub C. And now we're going to take the current going through this resistor, so we're going to go minus IR, and now we're back to our dot. So that was a pretty easy equation. Now, as we did in a previous video, we're going to change some of these variables. We're going to change the VC to Q over C, and we're going to change the I to dQ dt. I'm going to write the R first, but dQ over dt, and that's equal to 0. And once again, you can see that that is a differential equation because it has a variable as well as a derivative of that variable in it. Circle the correct answers here. For a discharging capacitor, that quantity, the charge per time, is on the decrease, which means that that is going to be a negative amount. Combining our equation with the fact that dq dt is actually a negative amount means that our equation will need to get modified so that it ends up looking like that. One more time, dq dt is a negative quantity, so that negative and that negative end up giving us a positive, so we are right about there, the process. Now we're going to solve this equation. We're going to put the quantity dt on the other side such that the equals 0 disappears. Let's do that. Q over C on the left, leaving us with, on the right, negative R dq dt. So we're going to manipulate part F so that we only have Q stuff on the right with dq in the numerator. What we're going to get then is on the right, we're going to have dq over q. And what will we have on the left? We'll have the dt in the numerator. There will be a negative sign, and then we'll have RC. So now we're going to rewrite that, showing our intention to integrate things. Let's integrate this side here from t equals 0. Whenever we discharge a capacitor, the time gets reset to 0. That's why t is still 0, and then there's some later time there, negative dt over RC. And since we're discharging a capacitor, the initial amount of charge is big Q. That's the total charge that's on the plate. And later there will be some lesser amount of charge, little q, dq over q. Okay, now we just need to integrate these answers. Nicely, we don't have to use U substitution this time. The left side is just going to give us negative t over RC. And the right side, the integral of dq over q is going to be the log of q. And we need to take into account those limits like that. Okay. The whole point was we were trying to get an equation for little q. It's tucked inside here. So let's e to the both sides this. All right, so let me show a little bit of work here. e to the both sides that thing, we get that. If we e to the both sides this, we just get little q over big Q. And so our equation for the amount of charge on the plates with time is going to be the initial amount of charge Q, big Q, e to the minus t over RC. All right, let's see if this makes a little bit of sense, and I think it does, because the charge on the plates should be falling, and we decided that if an equation had just e to the minus something, that it would be a falling graph or a decaying graph, and that is what we have right there.